these will be dynamic. Indirect blocks are pretty interesting, in that indirect blocks point to blocks that then point to data files. Data blocks, excuse me. So what's happening on a single indirect is we go off and we have a block, and it's the same size as the data blocks, and these contains pointers to data blocks. So let's think about how this works. A data block is going to have a particular size. For our purposes, we're going to pick 4K. And we're going to pick 4K, it's the same size as the page frame, and it's the same size as the virtual page, and it happens to be the page size that most file systems use. Okay. So if we're on a 32-bit system, right, so we have a 32-bit pointer here, and we're going to point to a 4K block, but the entries in that block are going to be pointers again. All right. How many pointers can I put? How many 32-bit pointers can I put in a 4K block? 4K divided by 4 is
1,000.
1K. See, what we do get, a lot of times people say 1,000. A K is 1,000 everywhere but computer science. Okay? Now, 1K though, doing it as 10 to the third is a fairly decent approximation if we have to use calculating file sizes. So if we have a single indirect block, okay, how much data can this single indirect block point to? How many know? Who wants to give it a shot? 4 megabytes. How did you come up with 4 megabytes?
1024 times 4K.
Yeah, so the blocks are 4K, and we have this intermediate block, which has 1,000 pointers, can point to 1024, to point to 1024 of these. Okay, and it's 4K page. So it's 4K times 1K, right? So it's going to give us 4 megabytes. Now, double indirect blocks point to a block that contains pointers, each of which points to a block that contains pointers. In other words, a double indirect block points to a block of pointers, each of which points to a single indirect block. Right? That's triple, sorry. Double indirect block. Okay? Each one of these looks just like a single indirect block. So how many, if we're using the double indirect blocks, how much space can we point to with the double indirect?
So just be 1K times 4 megabytes, right?
1K times 4 megabytes? No, that's going to be the single indirect. The double indirect. Okay, so the double indirect, each one of these blocks out here now is going to be 4 megabytes, isn't it? Because it's a 1K of pointers, each pointing to a 4K block. How many pointers do we have pointing to a single indirect? 4. How many pointers can we get in one of these blocks? 1K. So that would be 1K of these 1K blocks. Or 1K times 4 megabytes. Or 1K times 4 kilobytes, right? Okay. So if you take a look at it, a close look at it, you'll see that you get up into the gigabyte range, right? Probably around 4 gigabytes. Triple indirect blocks work similarly. So how much data can we point to with a triple indirect block?
4 terabytes?
4 terabytes. How'd you get 4 terabytes?
I just took it up an order of magnitude
3 orders of magnitude.
from the previous one.
Yeah, so what you did was you just saw that it was just doubly indirect blocks. Each one of these is one of those. Okay. Now, the way I walked you through that, whether you know it or not, is what I call the reverse method of calculating a file. I start with the data blocks. Say, okay, these are 4K, how many are pointed to it? Well, here it's 12. So this is 48K worth of direct blocks. Then we go into here and we have, we can get to 4 megabytes here. So we go, well actually 4K times 1K times 1. Then up there 4K times 1K times 1K. 4K times 1K times 1K times 1K. And then we have one of those pointers. If we were to approximate this, you would approximate it as about 4 terabytes. Because the next biggest chunk, which is 4 gigabytes, is 0.004 of a terabyte, isn't it? Okay. So it turns out looking at the triple indirect block gives us an approximation, a very good approximation for our maximum file, 4 terabytes. This was invented, okay, this inode structure was invented in around, I want to say 81 or 82. There was no such thing as a terabyte drive. Okay? And a file must exist on a single drive. Okay. So think about that. They were forward-looking. A friend of mine bought what did he say it was? 200 or 300 terabyte drive this past weekend for $313. That's cheap. And he's an I/O architect for IBM, so he doesn't buy bad disks. He's pretty good at his stuff. His name is Nerd. His real name is Michael, but he hasn't been called Michael since forever. The group of people he used to hang out with and was roommates with were the first people to bring the internet into Portland. It's now called Raindrop Labs. So they actually had like 5 T1 lines going into their house in the West Hills that they were renting. And they had a wall about like that little small square piece right there that was just full of switches. Nerds is sort of the way you look at that. So now, ordinary files we just talked about, this is how they're organized, and that's how they use. Okay, you can see a lot of this information, like owner info. You guys doing ls-l? Has anyone ever done ls-lg, which lists the groups that you belong to? Has anyone done ls-i or ls-li? Turns out that will give you a thing called the inode number. So associated with each inode is a number. Okay? So when we have information in a directory that says, oh, this file is located here, it's not pointing to a location on disk, it's pointing to an inode number. We load the number, and we'll see in a minute how we can quickly get to that inode, and then that inode tells us which disk blocks belong to the file and directory. Okay? Now, oddly enough, when it's a file you do an ls-l, the very first of the mode bits, which are the ones on the left-hand side, that some value, RWX, 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 the very first one, if it's a dash, it means it's a regular file. If it's a D, it means it's a directory. If it's a C or a B, it means it's a special file. Okay? So there's types information that's out there. And that's part of what, in this thing, they're calling it the mode. But the mode is really the permissions, but it also includes what's called the type. And T_dir means directory, T_file is a file, etc. Notice that it has a size, okay? And why would we put the size here when all we need to do is go through these blocks? Just count the number of blocks where the pointers are not null. Why do we stick the size in there?
You have a 4 terabyte file, it would be annoying to count it all up.
It certainly could, and really what you're implying by that is if we don't put the size there, once we get to indirect blocks, we're going to have to start doing more disk accesses to figure out how big the file is. Okay? So if we're just doing an ls-l, or we want to know the size of the file, as long as our file system is not corrupted, that size, which is usually measured in blocks, that size tells us all the information we need to know for an ls. Or a stat. Does anyone use the stat command? Okay, use stat a file or directory. There's a stat user command. And it's going to give you basically the same information as ls. Because it turns out that the stat command and ls both use the stat system call. And that is one that's worth playing around with right there. It's one of the reasons why I like to tell people to write their own ls command. You'll learn about the stat data structure. It's really, really cool. Then we have 3 timestamps. Okay, and these timestamps are important, but at the same time they're problematic. Okay, the 3 types are when it was the 3 timestamps are when it was created, the last time it was modified, and the last time it was accessed. Okay, and accessed means every time that we use a file or directory, we have to go back to its inode and update that time. So we'll see that that's actually one of the big performance problems we're going to have to deal with. All right, we'll talk about directories. Here's an example of a directory. Its inode, all it has is entries for directories, and it maps names to numbers. So this file 3 has this particular inode number, all right? And these are hard links because it translates name to number. If it translates name to path name, that becomes a soft or symbolic link. Okay. So the way these numbers get used is that at any particular point in time, a specific directory is actually located on a specific disk. Each disk contains inodes from 0 all the way to the maximum. Okay? Now, the inode number now is going to be relative to the disk. Each disk is going to have an inode 100. Notice that we don't say which disk it came from. Okay? We figure that out by information we already have stored when we mounted the disk. So if we go off and look at this number, we have to look at it on the current disk where this file or directory exists, where this directory inode is at. It cannot go to another device. And this is why we have hard links and soft links. They're called hard links when they point to an inode. And they're called soft links where we put a name out there, a path name. Okay? And that becomes important a little bit later on. So some common operations. Now, have you guys been using open, close, read, and write, or have you been using like fopen, fclose, fread, and fwrite? Is anybody using open, close, read, write? Someone use that one? Okay, that's the Unix interface. And we also have, the C library also has those now. They were added a few years ago, in 2011, I think. But it's not those map directly to read and write, open and close. fopen, fread, fwrite, those are formatted C library functions that will eventually call the correct underlying system calls to get your open, close, and reads and writes to work. On Unix, Linux, and Windows, anything that supports the Unix interface, they'll map to these particular operations. Okay, so if you want to read about these, you have to do man space 2 space open, close, read, write, etc. Sometimes we want to actually write into our file at a different place than where we opened it at. Okay? And to move around a file, we use a thing called lseek. There used to be a seek and an lseek. Now there's just lseek. And the one thing I like about lseek is this is where we can prove that the Unix file system was designed by people with PhDs and too much time on their hands. Because the arguments are, the last argument is called whence, which is a very old term. And here it's being made, it's really when we do the offset, it's relative to where. In other words, from whence we came is the phrase, which is very old English. Right? But, these guys, Rob Pike, I don't know if Rob Pike was the one that wrote this or not, but that's just kind of a quote, cute joke thrown in there. We did mention that a lot of things in Unix are based off really bad science fiction movies. Okay? And apparently somebody just enjoyed reading Victorian novels or something like that. And that's how we got lseek. But that's where we move ourselves around in our file. Has anyone ever here ever written a program that deals with something like graphics? Where you want to go out and change the color of a pixel? You can calculate where that information is stored at. Straightforward calculation. And then instead of reading the whole file and then writing it all back, you can just go to that location, load a couple of bytes, change the bits that you need to change, and write them back. Okay? You will have just grabbed data out of the middle of the file, modified it, put it back. Right? Stat and fstat are really, really cool. This is let's see, this is not the current Linux one. I think this is the current Unix stat buffer. And notice that when we get down here, this is an older one. It says the number of 512 byte blocks that were allocated. Some file systems use 512 bytes, most use 4K. Some use 8K. Okay? There's you could do them as a megabyte. Right? Not really going to change anything having to do with the inode, because you might have noticed that the inode structure that we drew there on the left is a fixed size. Okay? And the fixed size becomes important when we start looking at trying to get to the inode number. Now, unlike, yes?
I guess I'm just, is the stat data structure only used for getting this information about the file?
It only gets information about data on the disk. So it gets files, directories, special files, etc.
Okay, so we would only use that if we needed to gather that information, or do we use it a lot more often than we think?
Under the covers, it's being used all the time. When you do a CD to a new directory, it has to check the permissions to see if you can actually do that, if you're allowed to do it.
It'll go into the stat data structure and check that.
Yeah, it will call the kernel side version of stat, which is called stat-i. It'll get back that inode information, and it'll see what it is you're trying to do. It's like, for example, CD. And if you don't have the permissions to do that from the mode field of your inode, it will deny you. Okay. So, or ls. How many of you have found that you could, a lot of times, particularly here at KSU, that if someone gives you the full path to a file name, you can access that file, but you can't do an ls on the containing directory. Anyone discovered that? Okay. Different permissions. So links, there's a command called ln for creating links. And ln without any options will create a hard link, which means it can only put in a link from one object to another object on the same file system. Soft links can point to the same file system or across file systems because they use the path. All right? It could be a relative path, that is something that begins with dot or dot dot, or it could be an absolute path, and that's something that begins with slash. Okay? If you use tilde, how many of you use tilde when you're looking for data? Okay. If you create a link and use tilde, that's an absolute path name because tilde corresponds to your home directory, which for me would be /home/markEM. Okay. Which in itself is also a symbolic link. So, hard links, the way that they work now is the directories map, or the directory entry is going to be a name to an inode number. So when you do something like cd to /usr, we're checking the mode bits in USR. If you do an ls on /usr/foo, we have to check the mode bits on /usr, and then the file name as well. So there's several checks that have to go on in order to ensure that you're allowed. But it's a very flexible system. Okay? One thing to know is that inodes do reference counting. What do I mean by reference counting? Okay, reference counting in this case is it counts the number of hard links that point to that inode. So if we have two directories and each have an entry that points to inode X, then X will have a reference count of 2 because there are 2 hard links pointing to it. Okay? Well, and we know that because they're on the same disk and they point to that particular inode number. Soft links, however, do not reference count. And this is what makes them dangerous. Okay? With a hard link, when you delete a file that has a hard link to data on the disk, we don't delete the actual data. We don't delete the inode and its corresponding data blocks until something very special happens. And that is, every time we do a delete on a hard link,